Ελπίζω να με ακούτε. Ναι. Switching to English, I suppose, for recording purposes. So hello everyone here and from afar. I'm George Giannakopoulos and I'm very pleased to present as a host after some time, Themis Palpanas, a friend and colleague. Themis has quite a bio, quite a CV, and you can check the email that our communication team sent, and thank you very much for all the support. I will just summarize a few points that I think are worthwhile. Themis is an elected senior member of the French University Institute, which is a distinction that is horizontal across all disciplines. And I think it represents something like the top 3%, 5% of the whole academia in France. So this is a distinction that is similarly worthwhile. He's also a distinguished professor of computer science at the Université Paris Cité, France, okay. And he's the director of the Data Intelligence Institute of Paris and the director of the Data Management Group, Dino. Themis has held positions in several places, from Trento, where I met him, to the University of California at Riverside, IBM TJ Watson Research Center, Microsoft Research, and others. This is not the first time that Themis visits us, and but I'm always very happy to have him here. We will also have an opportunity to discuss with him after the end of the talk. Okay, for those of you who want to discuss after the talk, please nudge me when we finish here, and we can have short talks to initiate collaborations. So thank you very, very much, Themis.
Yeah. So thanks a lot for the kind introduction. I'm really happy to be back to Democritos. Thanks to George for organizing this, and also Faye and Irina. So I'm going to give you an overview of the work that we've been doing in the last few years on time series analytics. I'm going to focus on subsequence anomaly detection, but also spend a couple of minutes talking about similarity search in this kind of data series high-D vectors. Well, I would like to acknowledge a whole set of people that have worked in different projects in this area. And let me just introduce to you the problem setting. So we have one long time series, and we're interested in identifying subsequence anomalies. So identifying some subsequence of this series, which represents a behavior that is very different from all the rest. There are several different ways that we can define anomalies in time series. So we can talk about point anomalies or sequence anomalies. So in this particular case, that's an example of a point anomaly. And on the picture on the right, I'm showing you an example of a subsequence anomaly, where this subsequence here is very different from all the rest. What is important to note here is that if we look at these points of the time series as a set of points and examine the distribution of these points, it may very well be the case that the distribution of the points that participate in the anomalous subsequence fall within some normal limits thresholds in terms of point values. So what I'm trying to say here is that even though the points we're looking at individually fall within some normal limits, it's the sequence of points that may be anomalous. And in this case, it's this pattern, this high frequency zigzag pattern that is anomalous, because this is something that we do not expect to see in this kind of series. So in our case, we focus on this kind of subsequence anomalies, which go beyond and are more detailed, more informative, when compared to anomalies that we discover if we only look at the distribution of values or the values as or the absolute values in individual points. So these kind of anomalies, they appear in very different domains across different applications. So this is an example of an ECG, an electrocardiogram, where one of the heartbeats is anomalous. We have similar examples coming from several different other applications. So this is in energy consumption. We have also done. We have also collaborated with the French electricity company. So in their case, they wanted to monitor the operational health of an electricity production plant. And they are monitoring using sensors, several different components in this plant. And what we want to identify are anomalies in this operation. And of course, we want to identify these anomalies as soon as possible. So in our work, what we did was proposed different algorithms for unsupervised subsequence anomaly detection. The reason why unsupervised is very important in this case is because it's in general hard to come up with labeled datasets to train algorithms. And this is true because for two reasons. First of all, anomalies are very rare, so we don't usually find anomalies in existing datasets. And even in the case where we have anomalies, finding them, labeling them is extremely time-consuming. So it may take days worth of effort in order to label hours worth of data. So I said that there are different ways to define subsequence anomaly in anomalies in time series. One popular definition is the discord. So in this picture here, imagine that every point represents a time series. So we have a cloud of subsequences that are more or less similar to one another. There is this subsequence that is very different from all the rest. So we want to label this subsequence as an anomaly. So a discord is the subsequence of some given length, L, that is the most different to all the rest of the subsequences. So it's the subsequence with the furthest away nearest neighbor. And this allows us to identify anomalies in this way. There is a small problem when we have groups of anomalies. So in this case, the nearest neighbor is very close, yet all these subsequences are anomalies. So in order to address these kind of problems, the discord definition proposes to extend this definition to the third nearest neighbor. So in this case, we can identify these subsequences as anomalies when we look at the distance to their third nearest neighbor, right? So that will be outside this group of anomalies. Of course, this poses the problem of what of how do we choose the kth neighbor that we need to consider in order to identify those groups as anomalies.
Somehow reduce a couple of points or endpoint or a distance maybe more.
No. So in this entire, so the question was how we represent subsequences, whether we have to reduce them or not. So in this picture, so this is a conceptual picture. So every single point here is a subsequence. So every single point is a vector of L values. And then distances are, yeah, so distances are computed on these vectors. For example, Euclidean distance. Yeah, okay. So we have this problem with the Discord definition. And actually, when we have multiple similar anomalies, then we may end up identifying some false positives as well. So this is just a criticism to previous work in this area. So these are the different examples where the Discord definition leads to false positives. Yeah. So in this case, what happened? Right. So what happens here is that with the Discord definition, we identify. No, actually, we don't identify these anomalies. So these are anomalies. These are not identified because it's a group of anomalies that are similar. So we have 4 similar anomalies which are ignored by the Discord definition when we consider the distance to the first nearest neighbor. So when you ignore these distances, you will, of course, I mean, the Discord algorithm will still return one of these subsequences as the most probable anomaly. And in this case, it just happens to be this one. Okay. So, yeah.
Yes, perhaps it may help that, as far as I can understand, this resembles the traditional situation in the classic anomaly detection setting, where you can confuse the global outliers and ignore the collective local outliers. And I believe this is a similar case here, because we miss the collective 4, and we identify only one, which happens to be a false positive. This is how I understand it. I'm not sure it's...
Okay, but I'm not sure what it means, collective and contextual. So remember that in this case, we're always examining the entire blue series, right? So we don't look at a window of the blue series.
Correct, but when you're trying to identify the Discord, it seems that you are trying to locate one global outlier, which is a subsequence that deviates much from the rest of the data. And on the other hand, when you try to identify a cluster of outliers, of anomalous subsequences, it seems that they all lie inside a defined area in the space. So
no, this is not true. Maybe it was not clear in my discussion earlier. So in all cases, we look at the nearest neighbor, the first nearest neighbor or the kth nearest neighbor inside the entire blue series. So we do not select any subset here. Sorry? subsequences. Yeah. So we always look at subsequences of length L. So for every possible subsequence of length L, we look at the subsequence of length L anywhere else in the blue series with the kth distance to the original one. In any case, let me just once again say that this is what the previous work is doing, right? Okay, and we discussed this problem with the group anomalies. There are ways to avoid using the distance to the kth nearest neighbor. So for example, when processing some long time series, you can always do processing by looking only at the left of the current point. So this allows you to, so even if you have groups of similar anomalies, you can always discover the first anomaly. And then the second time that the similar anomaly will be appear in the dataset, it will not be discovered because it's similar to the first one. But we can still discover all similar instances by doing a similarity search using the first anomaly as the query pattern, right? So the very first time that we discover that one, we can do similarity search, identify all the other similar instances. However, the problem here is that you have to do this similarity search operation several times as you go along. So this adds execution cost. Yeah. Well, in general, what is an anomaly and what not is not very well defined, right? So there's no crisp definition, and in everything that I'm going to talk about today, the way that we deal with this problem is that we basically output an anomaly score. So the highest the score, the more probable to be an anomaly, but there is nothing that tells you what the right threshold is, right? So no one can tell us that. Sure. Yeah. Sure. We agree. Yeah. Yeah, that's true. Okay. Okay, so let's give you a brief overview of how the approaches that we have developed operate. So I'm going to briefly talk about two different approaches. Both of them are based on the following idea. We want given some time series to identify what the normal behavior is. And then we want to label as anomalies all subsequences that are far away from this normal behavior. And of course, what we want to do is build a model for this normal behavior and be able to build this model even if the data that we use to build this model contains anomalies. And this is why I mentioned earlier that the approaches that we propose are unsupervised. Because even though the data contain anomalies, we do not need to know anything about those when building our normal model. So there are two different ways to build this normal model. So one approach that we proposed is called NORMA. And the idea is the following. Once again, here, this is a conceptual view. So every point here is one subsequence. What we want to do is identify clusters of subsequences based on their similarity. And we can identify several of these clusters. And then what we want to do is define normal behavior as the aggregate of some of these clusters And some of these clusters means clusters that have high cardinality, clusters that are central. So they basically minimize some kind of distance to other clusters, and also clusters that contain subsequences that appear across the entire length of the series, right? So basically, what we're trying to do, and there are ways to formalize what I just mentioned. I think it's in the next slide. So we can formalize what I mentioned, and what I mentioned basically makes sure that we identify normal behavior as the set of subsequences that is relevant to the entire series, and it represents behavior that repeats itself often over time. Okay, and then of course when we compare this normal model to individual series, we can identify whether such a series is very distant from the normal model, or if it is close to the normal model. And this distance of individual series to the normal model defines the anomaly score. Right. So this is how this works. So we basically have our long series. We extract subsequences of some length nm. So this is the length of the normal model. So this length is usually greater than the length L of anomalies that we want to identify. And in that respect, it turns out that we can build our normal model for this kind of length, and then use our model to identify anomalies of different lengths that are smaller than the length of the normal of our model, right? So this picture here shows different clusters. So in bold is the average subsequence, and in lighter color you can see different subsequences that are members of this of each one of these clusters. So in this example we have 3 clusters, and the normal model is a weighted combination of these three clusters, and this weighted combination, as I said earlier, depends on the cardinality of its cluster, and also on the distribution of the subsequences in its cluster across the entire series. And then using the distance to this normal model, we can come up with this anomaly score. So for every single subsequences of the original sequence, we have an anomaly score that tells us whether each particular subsequence is an anomaly or not. Okay. So this is very briefly how this works. Let me skip these slides. So this is what I mentioned earlier on how we build how we select the clusters for the normal model. And now a different way of solving this problem. It's an approach that we developed, and it's called series to graph. So this is a new representation for time series that represents a long series as a graph where nodes are subsequences and edges represent paths in the original sequence from one node to another. So let's see how this works. Once again, we have the same picture. Like I said, we're going to construct a graph that represents our long series. So in this graph, we have nodes. Every node contains a set of similar subsequences, no matter where they appear in the long series. And we have edges between nodes in the graph. So this edge here means that there is some subsequence in this node that has followed this subsequence, some subsequence in this node in our original series. Okay, and you can immediately see that having such a graph, we can once again identify what is normal behavior. So normal are basically nodes that have a high cardinality and edges that have high weights. The weight of an edge is determined by the number of times that we have some subsequence here, that some subsequence here has followed some subsequence here in the original series. So these kind of transitions in the original series have happened lots of time, right? So so paths that involve edges with large weights correspond to normal behavior, and paths that involve edges with very small weights correspond to abnormal transitions, transitions that have happened a few times in the original sequence, and therefore correspond to abnormal behavior.
This is very intuitive. So essentially here we move the importance from the nodes themselves, from individual subsequences, to changes or whatever, transitions from subsequence type to subsequence type.
Right.
So it's a longer term, let's say, phenomenon that we study here.
Right.
Right, and a different type. So we don't care about specific local phenomena, but the transitions. So essentially you define normality here as longer subsequences of similar types. This is fine, just to double check this was. And one more thing, essentially here you, however, normal groups, or let's say
So think of this as follows. Let me also say that the length of these subsequences in this case that we use to build this series to graph representation, the length of these subsequences is smaller than the length of the anomalies that we're looking for, right? So basically, paths in this normal behavior correspond to several small subsequences that put together construct some longer sequence that occurs frequently, approximately the same, in our original series.
One more comment here is that the fact that nodes with high value incoming edges may correspond to the central, to the model you had in your previous approach, right? So they are subsequences shorter, as you said. So I'm not sure it's exactly the same. Because,
yeah, it's not clear to me. Yeah.
Because this strong incoming edges, if strong enough, which is it means that they have high cardinality across the whole signal, whatever, most probably. I'm not sure it has sentence.
Yeah.
I'm not sure it has sentence that it happens everywhere. This is another story.
Yeah.
But say that's
So
common enough.
Yeah. So that's a good question. I'm not sure if there is a one-to-one correspondence with what I was describing earlier. So then the nature of the representation here is different. Also the elements, these subsequences that are smaller are different. So I'm not sure if this correspondence is there. So let's see. Right. So as I said, the length that we use here for every single subsequence is less than the length of the anomalies that we're looking for. And in practice, we can build, once again, we can build this model once, and we can use it to identify anomalies of different lengths. So in this particular case, we can identify anomalies that have the same length as this subsequence, that have lengths between this length and 4 times this length. Right? So this gives us lots of flexibility at analysis time to identify anomalies of several different kinds.
So may I ask something? Do we care in each of these clusters about the order of the subsequences that are inside there? Or we do not care? Each cluster it would have.
No, we don't care.
Is that important? I wonder.
Yeah, so why would that be important?
I don't know. I'm wondering because I feel that we miss some kind of information here, and I wonder if it is important to the whole procedure.
I cannot immediately see how, at least not in the way that the algorithm works now. But maybe this will have an impact if we came up with a slightly different algorithm. Remember that the ordering is captured inside each one of these points. So each one of these points is a subsequence, the ordering is there. We have no information about whether this subsequence, about where in the series each one of these subsequences appear. We have the information, but we do not use it in the node. Yeah, so it's not clear to me. So maybe a different algorithm could make use of this information as well. Yeah, exactly. So this subsequence has come after this one in the original series.
One of these.
Okay. What I understand, just make sure that I understand correctly, is that when there is an arrow from one cluster to the other, then one of those subsequences, any of those subsequences in the first cluster, is followed by any of the subsequences in the second cluster.
Right.
So, and there are many cases where we have seen one of those subsequences followed by one of the others.
Right.
But we don't know exactly which one from the cluster.
We can find out.
But
Yeah,
we don't care about it.
we don't care, right?
Yeah.
Right.
But still, I don't understand how you define anomaly.
So, so the anomaly. Do I have a slide? The anomaly is identified by paths that have very small weights.
But
So
how long should this path be?
It depends on what the user asks for. So the user comes up with a length L of anomalies that they're looking for. So for this particular length L, we can identify all the paths that have very small weights. So for example, if the length that we have used here is 10, and the user is interested in anomalies of length 15, so we use paths of size 5, because every transition adds one more point. So these things are overlapping, right? These subsequences.
I understand that they're overlapping, but I'm not quite sure that a path of length 5 involving 5 clusters necessarily corresponds to something of length 15.
Yeah, it does, because a continuous path of length 5 means that in the original series, we have a subsequence of length 10, followed by another one of 10, followed by another one 5 times. So the length of the resulting path of 5 is 15.
My problem is that each of those nodes is a cluster.
Right.
Which means that it doesn't correspond necessarily. What I observe on the graph does not necessarily correspond to a sequence.
So you're saying that we may not have a single sequence of 15. Yeah, you're right. Yeah, this is true. That's true. But in any case, let me just go to the next slide. So basically, what happens here is that we do preserve a mapping between the graph and the original series. And then this can always get you back to the original subsequences that do appear in the series. So let me just quickly tell you how this works. So giving the original series, we extract all possible subsequences. All these are represented by some paths. So in this case, every single point here is one of the subsequences. And all these points are all possible subsequences, right? And there is a single path here that starts from the beginning and goes to the end, right? So there is a single line, okay? So this is a PCA embedding of all these subsequences in 3 dimensions. Then, as a first step, we look at a 2-dimensional representation of this PCA embedding by removing the direction that corresponds to scaling in the different subsequences. And then what we do, the way that we transform this picture, this representation into a graph is the following. We consider the space of these embeddings, and then we look at different directions in this space. So we look at a finite number of such directions. I don't recall how many of those we examined. And these are the directions psi. And for every such direction, we look at all the intersections to these trajectories. Okay, and these intersections, they form a distribution, and this distribution tells us how many nodes we're going to need to represent all these embeddings. So in this particular case, we have a single node. In this other case, we have a bimodal distribution, so we use 2 nodes. Okay, and you can see that here there is a subsequence here that follows a subsequence in this node. Okay, so in the resulting graph, there will be a path that corresponds to a real path in the original series. Okay. Right. And right. And this is another example of how this works. So we have the original series. This series corresponds to this kind of paths. And it also corresponds to a path in the final graph. Right. Okay. So did I convince you?
This is different. This is different from what I understood before.
Okay.
Yeah, I mean, here I say what
Okay.
is happening, but
Yeah.
is it related to what I was saying?
Well, this is what happens.
Maybe the conceptual representation
Okay.
is very abstract.
Okay. Yeah. Right. So how do we choose the length L? Yeah. So how do we choose the length L? We're interested in identifying anomalies of length L. So this is what the expert user will give us as input. Then, as I mentioned, the series to graph representation will be built with a smaller L, and this will allow us, to then discover anomalies of L, L divided by 2, L times 2, so with wide range. No. We pick one smaller length to build our representation. Based on this smaller length, we can then analyze the graph and identify anomalies of several different lengths.
How much smaller is that?
So, yeah. So in our experiments, we started with a given L. We started with how do we call it? LQ. We started with a length LQ to build the representation, and we did experiments in detecting anomalies with lengths LQ up to 4 times LQ. And it worked well. Okay. Okay, so as you may imagine, there are several different algorithms that have been proposed, dozens of algorithms for anomaly detection in time series. So we did an experimental evaluation with several of them. And here I'm showing you the results for norma and series to graph. These are the highlighted numbers for different algorithms, and we measure precision at k. So the higher the number, the more accurate. So you can see that series to graph and norma lead to the best accuracy. So this is significantly better than other methods. Interestingly enough, also significantly better than supervised or semi-supervised methods. So just one comment here. So there is lots of work in the last couple of years on anomaly detection methods based on deep learning. Most of these studies, they do not compare to traditional, to non-deep learning algorithms. And this is a big mistake. As I will also mention later, there is yet a deep learning method that overall performs better than traditional non-deep learning algorithms.
So in the evaluation, although you're there already, so you provide a score per instance. That's what you do. So you assign a score per subsequence. Sorry.
I will come back to that. Yeah. So the labels that we have are labels on subsequences.
Excellent. And the labels are numbers or outlier, not outlier.
It's a binary value.
It's a binary value. So there is a thresholding process somewhere, or not?
No, these labels come from some expert, right?
No,
So
this
is ground
the
truth.
standard mean there is a ground truth. Yes, but I'm trying to understand how you assign. So if it's precision at some at k,
precision
yes,
k in this particular case, we were looking at the k top anomalies identified by each algorithm, and for each one of these k anomalies, we saw how many of those were true anomalies.
Excellent. So you examine different k values, or did you select one? I'm trying to understand what there
Right.
sample bias.
Good question. No, I think that we had different case. I don't remember what this.
This might change a lot. That's what I'm thinking.
Yeah, no, we tried out a different case. Yeah,
Okay.
but I will come back to this point.
Are you considering something correct if it's an exact match only, or if it's a subsequence?
So this is the point that I want to discuss later on. I don't remember how exactly we did it here, but what you mentioned is a very good point. So yeah, so let me come back to this point. And at the same time, the algorithms that we propose are much faster than the state of the art. So in this case, we have on the x-axis the number of points, the number of anomalies, and the anomaly length. On the y-axis, we measure time, so lower is faster. So this is exactly what we were discussing now. So thanks for the question. So we talk about having ground truths. And what is a ground truth here? So some experts said that this subsequence here is an anomaly. Okay, all anomaly detection algorithms propose output some anomaly score, and based on the anomaly score, we need to set some kind of threshold and identify as anomalies everything that is above this threshold. And then there are different issues here. So one issue is where do you set this threshold, right? So based on this, you can make some algorithm look very good or very bad. It is also the case that the anomaly score may or may not correspond well with the labels. So this was your question. And in such cases, the question is, how do we score this kind of output? Right. So if we are very strict, we can say that this part here is true positives, but then these other parts are false positives for false negatives. So this kind of evaluation suddenly becomes very tricky. And all this is very important because this is a practical problem, and it does not allow us to very accurately form an opinion about which algorithm is better than another. And then there was right. And then this is the problem that I mentioned earlier with setting the threshold. So depending on the point at which we set the threshold, we have a different point in this graph of true positive rate and false positive rate. So in general, for this kind of algorithm evaluation, we want to use OCROC measures. So this is something that has been proposed in the past.
How do you measure true positive rate and false positive rate here?
So this was based on what I showed you earlier.
With the method that, so it's basically time point based. So
yeah, exactly.
You're counting the number of anomalous time points that have been found.
Exactly. But right, yeah. But even that is not exactly what we would like to do, and this is because the labels themselves, even though they are labeled by experts, they are not always true or accurate. So, for example, some expert may label this anomaly at this point because this is where it starts. Some other expert may label it there because this is I don't know. This is where it has the anomaly right in the middle of the window, right? So even the labels that we have are not very accurate, which means that all this evaluation is subject to these inaccuracies of the labels, which definitely exist there, because there is no standard way of labeling anomalies. So in order to account for all these different variables on how we evaluate these algorithms, we also proposed the views measure. So it's volume under the surface, which is basically a no-croc measure that also takes into account this inaccuracy of the labels. And we also worked on a very large benchmark on evaluating I think, hundreds of different anomaly detection methods. So this is the TSB univariate anomaly detection time series benchmark, univariate anomaly detection. So if you're interested, you can find the code for all of that on GitHub. So there is code that for all these different algorithms. There are also several different, basically all different datasets that have been used in this area for anomaly detection. And this also includes code for the views accuracy measure. So basically, the point here, the overall conclusion is that there is no overall winner. So there is no single method that performs the best across datasets with different characteristics or anomalies with different characteristics. So, for example, subsequence or point anomalies. And this is why one interesting direction forward is model selection. So if we have all these different models, if we have different models that have a different performance for data sets with different characteristics, how can given some data set select the model that we should use? And here you can actually see what is the accuracy when we use different anomaly detectors, the average accuracy across all data sets. And this green bar here shows what is the accuracy of of an average ensembler, right? So this method here is the average ensembler of all these methods. This increases accuracy a little bit over the best detector. It is significantly better than the average of these. Well, it's right than the average of these detectors. But on the downside, it requires lots of time to execute. So this is execution time. And the reason is because the average ensembler needs to execute all these algorithms. In contrast, if we focus on accuracy, we can see that if we have an oracle, so this oracle here always picks the best detector for each dataset. So you can see that the oracle can do much better than our current detectors and the average ensembler. And this leaves lots of space for doing model selection. So we had a paper published last year, and this achieves this kind of behavior for the model selection. So it's significantly better than the average ensembler, and also significantly faster. But you can see that there is still lots of room for improvement. In addition, this model selection tool that we have proposed works well if the new time series that you want to check for anomaly detection is similar to one of the ones that you have trained on. If it comes from a completely new domain, then it will not perform better than the average on ensembler, right? So there is still lots of room for interesting work in this area. Okay. So let me just spend 1 minute to talk to you about this other problem, which is similarity search on time series and high dimensional vectors. So this is also a problem on which we have been spending quite a bit of effort. So similarity search is very important because it's at the core of several different data analysis algorithms. but it's also extremely hard to do when we talk about very high dimensional vectors and very large collections of such vectors. There are several different flavors of similarity search, ranging from exact to approximate with deterministic or probabilistic guarantees, all the way to approximate with no guarantees whatsoever. Even approximate with no guarantees algorithms are extremely important because there are several applications that are interested in very fast execution times. So these are much faster than those. And at the same time, even though they do not have any guarantees, in practice, they invariably perform extremely well. So the answers that they return are very close to the exact answers. So in this case as well, we have proposed several different algorithms. Oops. And basically, there was a huge reduction in time execution as we started back like 10, 15 years ago with the very first similarity search indexes for large collections of time series. But now we have moved to indexes that can support all these different kinds of similarity search that I mentioned earlier. They can support both Euclidean and dynamic time warping using the same index. And since some of these indexes use modern hardware, so multi-core, multi-socket, also if the dataset fits in main memory, then we can achieve very fast similarity search times that are up to 5-6 orders of magnitude faster than what we started from. And what is extremely interesting is that all this also applies to general high dimensional vectors. So time series on which these indexes were first developed for are nothing else but high dimensional vectors. And also we have now high dimensional vectors as deep embeddings, right? So we can represent as a deep embedding high dimensional vector any kind of object, and then do complex analytics on the deep embeddings that are direct proxies of the original objects. So this makes the analysis much faster, much easier. So what I'm trying to say here is that there is lots of interest in doing similarity search in general high dimensional vectors, and for all sorts of different applications. And it turns out that among all the different techniques that have been proposed in this area, the techniques that originated from the data series community, so the techniques that we have worked on are the best for approximate queries with probabilistic guarantees, are the best for very long vectors, and probably the only viable solution when you have on-disk datasets. So I will be happy to talk to you on this subject as well. So just to conclude, we addressed the problem of detecting anomalous subsequences within a long data series. So this is an important problem with many applications. We proposed techniques that are unsupervised and scalable, both of these very important requirements for modern applications. And well, there are still several open research directions. I talked about univariate series, but a very interesting question is what happens when we move to multivariate series. So how do these techniques carry over? And also, how do we design evaluation measures, benchmarks, AutoML tools, etc.? We're of course open to collaborations on all these topics. We're located in the center of Paris. That's the Data Intensive and Knowledge Oriented Systems group. And you may not you may not know it, but apart from collaborations, there are also other interesting reasons for visiting us in Paris. So we're very happy to host you there as well. And thank you very much. If you have any more questions.
This is the case of time series with regular intervals. I mean, interval where it's the two consecutive time points do not have the same always interval. So in this case, I guess it becomes a more complicated how to define like an anomaly.
Right. Yeah. That's a very good question. No, we have not. So we assume regular time intervals. So what usually people do is that in these cases is that they normalize to some the sampling rate, either oversampling or undersampling, using data imputation, etc. Yeah.
Thank you again. There's a lot of information, and the number of questions has been increasing with every slide that you presented. But I will start from the beginning. It seems to me that the choice of distance is very critical. In one of the real examples that you showed at the beginning, it seems to me, maybe I'm wrong, that the reason why something is an anomaly does not have to do with the subsequence at all. So you may have a very normal subsequence placed in the wrong position. So the place where the subsequence occurs may be the reason why it is anomalous, rather than the content. So it's more context than content. And I think this, to some extent, may be captured by transitions in the graph. I'm not sure if it can be captured in all cases, but it could be captured by changing the distance measure. Are there distance measures that take context into account rather than content?
So in all these works, people use Euclidean distance. You can use any kind of distance, but for example, consider what happens if you use dynamic time warping. So in this case, you may not be able to capture differences on the speed of the different phenomena, which may be important for anomalies. So in general, people here use Euclidean distance. This contextual anomaly that you mentioned, this is a very good point. So you can capture such anomalies if your anomaly, if the length of the anomalies that you're looking for is larger than this subsequence that you mentioned, right? So if the length that you're looking at is large enough to contain also the context, then you can capture this as an anomaly.
I can understand that, but if in order to do that, you may have to go to very large length. So you consider something that is a sequence of smaller subsequences, and you have let's label them A, B, C, D, E, and you have so then this appears again and again. A, B, C, D, E, A, B, C, D, E, A, B, C, D, E, and at some point you get A, B, C, D, E, E. You get two E's.
Right.
In order to be able to capture that, you have to have something that is long enough to capture the whole A, B, C, D, E.
No. You just need the length of two letters.
E, which is not the case.
Right.
But you may have EEs in normal sequences as well.
Yeah, but in case you see my point here, right? So you have to so your anomaly length has to have enough information for the anomaly to become apparent. Yeah, so this is true.
And I think you mentioned you have some, the reason why I thought of that is because you had some very good examples where the anomaly was what you didn't observe rather than what you did observe. So you would expect to observe a peak, but you didn't have no peak.
Okay.
But what you observe is something very frequent. But it shouldn't be, but at that point, there shouldn't be something very frequent. We should have something that is less frequent, but very regular. So,
Yeah, we agree.
Quick point on my side, one side, my side, sorry. Okay, I see a lot of methods, and as I said, intuitively, they make sense to me. The only problem I see is that increasingly you add more questions you have to ask for individual steps. So starting from the what distance do we use, or even going before that, you have already embedded your sequences into a feature space, right? How do we embed this? So the one challenge I see, which is not a bad thing on itself, if you have a palette of options, but anyway, so besides model selection itself, you have lots of steps and lots of parameters from the original embedding space to the distance, to the sequence length, to the evaluation measure overall. So I see many opportunities, to be honest, to examine which things are better for what cases. Going back to the last part of your talk, where you said that these ensemble methods and trying to combine things, one question I would ask myself, and I think we have done this together some time ago, back in 2009, is how do you define a problem setting so that you can do informed model selection? By how do you measure, how do you position in a space the problem you are trying to solve, so that this might guide you in what parameters, what models to utilize, what method to utilize to solve it the best. So this kind of expressing the problem in itself you're trying to pose, I think would be a significant opportunity to do it in a supervised learning, this model selection, to do it in a supervised.
No, but this, okay, so let me answer to the first question on the parameters of the methods. So both these methods, norm and series to graph, essentially only have one parameter. So we ask the users for one parameter, the length of the anomaly that they're looking for. And everything else, we have default parameters that we know how to set. And by using these default parameters in different benchmarks that have been proposed, both these algorithms are among the very top performers. In terms of the model selection part, the technique that we developed is supervised, of course, right? And it tries to do exactly that. So identify different different features that would allow us to connect algorithms to data characteristics. So we have not done a detailed study there. So we just used off-the-shelf feature extractors and then thrown in a whole bunch of classifiers, try to come up with some classifier that gives good results. So I don't have much to tell there on how we can come up with good features. So I also mentioned that our model selection solution does not work for new kinds of data. So I'm sure that by doing a more careful job on characterizing this search space would allow us to then make more informed decisions. So yeah, so there is lots of work to be done there.
Thank you very much for your presentation. It's another reason for regret not being younger, since I've worked with that for more than 20 years. Okay, so probably I would like to make a comment in this discussion now with Yorgos and Yorgos. When you have a specific use case, let's take an investment management company, okay? the threshold setting by the user, by the expert is very important, depending on the parameters you use. But for example, one parameter for the investment management company is the time that the money stays within the program. Another one is the amount invested. A third one is the return the amount the investor has after a certain time. So in these cases, it's true that you have different anomalies when you detect such series of transactions. But when you make a cross-section with using all these parameters or combination of these parameters, you find the real anomalies. So I believe that the thing that you are trying to show us is much more difficult when you use one parameter in order to explain anomalies. And this is why, probably because creating some questions, additional questions, depending on the size of length and things like that. The criteria used as parameters for detecting anomalies are different for every bunch of data sets. It's different from retail. For retail, it's different from investment, different for energy consumption, etc.
I agree. This is true. So we definitely need, I mean, all these techniques, they definitely need to operate closely with the domain expert, because that's the only way that you can understand what's happening and also use them in the best way. And of course, another thing, once again, is that depending on the characteristics of the data, determined by the domain and the application, different techniques among all the ones that have been proposed in the literature may be the best choice. Yeah, definitely.
I have many questions. I want to understand a bit better what you said near the end, where you talked about the application of time series, if I understand correctly, the application of the time series search on embeddings from wherever the embeddings may come from. Is that what you meant?
Yeah, exactly. So basically what I mentioned was the following. I said that well, these are different similarity search methods, right? And these are similarity search methods that have been proposed for high-dimensional vectors, that have been proposed for what? For time series, that have been proposed for multidimensional data, right? So what I was saying was that in all these cases, these methods, they basically do similarity search on high-dimensional vectors. No matter if we call them time series or deep embeddings or multidimensional data, in all these cases, these are high-div vectors. And you can apply any of these methods on all these different datasets. And what I'm saying, yeah, and what we have demonstrated is that the techniques that were originally developed for time series, they are the best performers for general high-div vector datasets as well.
Although in some cases, those vectors don't have an order.
Exactly. Yeah, exactly.
Because you could also see it the other way around. Many of those vectors come from sequences. For instance, take language or videos. They are sequences. And we extract embeddings, so we remove the order.
Yeah, but these embeddings, they do not encode any kind of order, do they?
That's what I'm saying. We remove the order.
Right.
And we get an unordered vector.
Right.
And you could do the same for time series.
Yeah, exactly. Yeah.
You can do the same for time series and you can get embedded.
Right.
And so what you're saying is very interesting in that there is a duality between applying time series methods to unordered vectors or other methods sequence.
Okay, yeah. What I'm saying is that you can forget the order. If you forget the order, so the order is not formalized in any of these methods or representations. The order is conceptually there. We know it's there, but I mean, none of the methods does anything specific about the order. Even the time series methods, where we conceptually have this order in mind. So you can get your time series data set. Think of it as a table, right? So every row is one time series, every column is one timestamp, right? So when you have this table, you can rearrange the columns, right? Rearrange all the columns in a random order. Nothing will change. You apply the same algorithms, they will give you exactly the same results. Nothing changes. And
I don't believe that yet. I have to convince me.
Eh? But in any case, so what I'm saying is that well, okay. So all these data points are high-dimensional vectors, and all these techniques have been proposed to operate on high-dimensional vectors, right? Whether there is sequence information or not. These are techniques on high-dimensional vectors. You can apply any of these techniques to any kind of time series or high-D vectors or deep embeddings or multidimensional points or whatever. You can do that. Well, if you do that, and we've done an extensive experimental comparison, it turns out that the techniques that we've been developing for data series, they are the best performers across the board. So for both on disk and in memory, for both exact and approximate, the only so for most of these sub-problems, the data series techniques are the only viable solution. So for example, for on-disk data, even more importantly for exact queries, even for approximate queries with guarantees, even in that case, these techniques are much better than the data series indexes are much better than any other solution. So, for example, LSH, it does not work. It requires orders of magnitude more space, and it's much slower. What was I saying? Right. So the only sub-problem in which some other technique performs close to data series is in-memory datasets, approximate with no guarantees. And this is the guy, HNSW. But even in that case, so last year we proposed this method called LPs. So this is a technique for similarity search for in-memory approximate no guarantees. So this is based, so this is a hybrid method that uses some ideas from HNSW and some ideas from the data series kind of tree indexes. And this is a much better solution than HNSW. And once again, let me say that this kind of similarity search for deep embedding vectors is extremely popular. So it's nowadays used everywhere. So search engines use this to improve their search results. Facebook uses this to check for duplicate images when users upload images. The same for videos. Facebook has many applications based on this to do similarity search, recommendation, whatever. It's also used a lot in other disciplines. So, for example, molecules do similarity search in the molecules. So it's a core operation in many different use cases.
When you say graph-based similarity, do you mean graph as in the graphs you showed in the sequence of
When I say what?
in the bottom at the bottom you say graph-based similarity. Do you mean
No. This is yeah. Sorry. This is no. This is a different representation. So this is relevant to HNSW. If you, so HNSW and LPs using some of these ideas is based on the KNN KNN graph representation. So this is a representation where you have a graph. Every node of the graph is one high-dimensional vector, and every node of the graph is connected to some of its nearest neighbors. And this is the graph. And then you can use such a graph to find, to do similarity search, right? Because you fall in some position in this graph, and then you travel to the direction that minimizes you, that reduces your distance.
basically not very far from what you're doing because it is a similarity. It's the same similarity.
I don't think it's no. I don't think it's the same.
But you don't have cluster. The main difference is that you don't have node clusters. You don't have cluster nodes. You have.
Well, you don't have clusters. You don't have this. No. It's very different because the series to graph is a representation of subsequences of a long series, and how these subsequences are arranged in the long series. This is why we have paths in our series to graph representation. In this case, there are no paths. In this case, you have high-dimensional vectors. So there is no long series. You have high-dimensional vectors, individual subsequences.
You are. I think what you're doing is that you are having an analog between the high-dimensional vectors and the series. I make an analog between the high-dimensional vector and the subsequence.
And the subsequence, yeah, okay.
So
But in one case, subsequences are related to one another. They're overlapping. In this case, they're not. They don't have to be, yeah. And in any case, in our series to graph representation, we also use this intermediate embedding step. There is no embedding here. So anyways, this representation is different. I mean, we cannot use series to graph to do this, to do similarity search.
But it is a similarity. There's no other information. No, it's not similarity.
Yeah, similarity. Yeah, right. Yeah.
Should I suggest that we close the session so that we release people and we follow up with those with target discussions?
Yeah, thanks for the many interesting questions.
And there is more, you know.
Thank you.
So any follow-ups? Just when we start, you know,